Thank you very much for coming tonight to this panel discussion on 1,4-dioxane and Acton's water. I want to emphasize that tonight is an educational event. We're not here to try to solve a specific problem or make any kind of decision. The goal of tonight's event is for us to learn, to increase our knowledge base as individuals and as a community, so that as this emerging situation develops in the future, we'll have more knowledge and more understanding from which to take action, on which to make decisions. Tonight's event is brought to you by Green Acton, which is a local environmental advocacy organization, and the Acton Area League of Women Voters. And I should thank the town of Acton, which is providing the venue, and ActonTV. This is Patrick, sorry. This is Patrick. Patrick is going to be filming for ActonTV. We are not broadcasting live. However, the event will be available from the ActonTV website in the future. So if you do speak, your voice will be recorded. The plan for the evening is that we have 3 expert panelists. They'll each speak for about 10 minutes. Then we'll open the floor for questions. And I'd like to ask you to hold your questions until the end of the speakers. So I've been through all the slides, and I'm pretty sure that a question that might emerge early in the sequence would be answered by a later speaker, so we'll have all our questions after all 3 speakers have spoken. We have a lot of time for Q&A at the end, and so I'm pretty sure we'll get to everybody's questions. So a little bit about what we're going to hear about. Our first speaker is going to be Matt Mosteller. Excuse me?
Who are you?
I am Kim Castens. I am your moderator for the evening. I am the chair of Green Acton's Water Committee. I'm also a scientist emeritus from Lamont Dougherty Earth Observatory, which is the Earth Science Lab of Columbia University. And I live in Acton. Kim Castens, K-A-S-T-E-N-S. So our speakers, yes, I don't have a label, but Kim Castens, that is me. Our first speaker will be Matt Mosteller. Matt will help us understand where the 1,4-dioxane is coming from in the area, how it travels through the groundwater, how much is in Acton's water. And I should say that at the beginning of each speaker's talk, they'll tell you a little bit about their biography and where they work and what they know about in particular. Our second speaker will be Diane Manganaro. We'll explain how the Office of Research and Standards at the Massachusetts Department of Environmental Protection sets guidelines for contaminants in drinking water, what's known about the health effects of 1,4-dioxane in water, and what the guideline is that Mass DEP has set for 1,4-dioxane in water. And then finally, Matt Grower will help us understand what's currently being done about the problem, what's being done as far as trying to intercept and divert and then ultimately treat the water before it travels through the groundwater and the dioxin reaches our water wells, public water wells. So I'll be the moderator. I already told you who I am. I think we're ready to go. So, yeah. Get your slides.
Sure. And while Kim does that, you just use shorthand, and it sounded like dioxin, and just to be clear, it is very different than the chemical known as dioxin.
Same. Okay. Thank you. Yes.
You're welcome.
1,4-dioxane with an E, with an A and E.
Yes, correct.
It's not up here.
I try not to use it.
Yeah.
So, thank you, Kim. So, very quickly, who I am and why I'm here. Kim set that up. Really, my name's Matthew Mosteller. I'm the environmental manager for the Acton Water District. I've been the district's lead on 1,4-dioxane since I came to work for the district in 2009. I have a Bachelor of Science in Environmental Science. I have a Master's in Public Administration. I'm a licensed drinking water treatment operator, and I also represent water suppliers on Mass DEP's Waste Site Cleanup Advisory Committee. And I've been very passionate about this issue for a number of years now. And I'm really here to talk to you about where the 1,4-dioxane is relative to our drinking water wells, how it got there, and how much we currently are seeing in our treated water here in Acton. Because, full disclosure, we do have concentrations of 1,4-dioxane in our drinking water. There are other people in this room that have greater knowledge about hydrogeology than I do. They have greater knowledge on the history of the W.R. Grace site than I do. But I'm going to try and really put this into the context of how it all relates to 1,4-dioxane. And apparently, this is self-advancing. You warned me about that.
I did advance myself.
So I'll give you a little bit of the district's experience with 1,4-dioxane. Talk about the W.R. Grace Superfund site. That is one of the places that this contaminant is coming from. Talk about something called the UCMR3. Everyone tells me I need to define that. That would take up 2 more slides to do, so I promise I'll let you in on that in a few minutes. Then talk about the Nuclear Metals Superfund site, which is located on the Acton-Concord town line, and then I'll wrap up with our current concentrations. So, speaking from the district's experience, back in, wow, this thing is finicky.
You know what, you can use these forwards and backs.
Can I?
It might be a little bit
Okay.
less.
I'm going to stick this down here. I should have learned my lesson 2 weeks ago. So, speaking from experience, back in 2006, W.R. Grace was asked to collect 1,4-dioxane samples because it was what's known as an emerging contaminant. And they wanted to understand what, if any, concentrations of 1,4-dioxane were at that site. The reason they wanted to do that is because 1,4-dioxane is in what we call chlorinated solvents. Historically, that was used at the Grace site, and that was the majority of what has been cleaned up and continues to be cleaned up at that site over the past 40 years. Their concentrations during their initial round were below the method detection limit, which was 2 parts per billion at the time, and they went as high as 36 parts per billion during that sampling round. At the same time, EPA asked the water district to test its production wells. We have 5 of them in the area of the W.R. Grace site. So we sampled those in 2006. 2007, we wanted to do a pump test to take one of the old W.R. Grace production wells and try to convert that into a drinking water supply well. So we did some pump testing there. Mass DEP said, if you're going to use this, you need to sample. And at that time, when we, just prior to shutting down the test, we saw a concentration of 0.56 micrograms per liter, parts per billion. And really, that was the highest concentration we had seen. And the reason that was the highest concentration we had seen is because between 2006 and 2007, the method detection limits, what the laboratories could do, was starting to improve. And this is going to be a common theme as we move through the history here. So once we knew that we had concentrations of 1,4-dioxane, we needed to understand many different things about that. At the time, the guidance in Massachusetts was at 3 parts per billion, which was much higher than the concentrations that we had seen in our wells. We virtually thought that we had non-detect. So we needed to do a bunch of things. The map that you see here was something that we had to draw out by hand because the site management team for W.R. Grace hadn't really put all this information together. So we started to plot this out on our own by hand. We needed to understand how our groundwater protection zoning fit into where we thought there were going to be concentrations. We needed to use other people's groundwater modeling. So one thing that we've had a lot of work done here in Acton is to understand the aquifers. We wanted to understand how contaminants were moving around at the Grace site. And one of the things that we as a district did is we relied on some of the modeling work that other parties had done. When you're doing modeling, when you're talking about hydrogeology, you need to make assumptions about what's going to be a hydraulic boundary. So a place where water is going to flow in one direction but not in another direction, where it might discharge. Commonly, things like changes in subsurface material are going to be a hydraulic boundary. If you have a surface water feature, that could also be considered a hydraulic boundary. We need to understand the implications of bedrock in this area. In a few slides, you'll see more about that. I think someone's in the back switching the slides. And we also needed to understand that if we were seeing all these yellow dots, how was it this spread out? Was there more than one source? Was there one source that somehow was making its way around? And really, we needed a bigger picture perspective on what was going on here. So very quickly, I talked a little bit about groundwater and understanding aquifers. This is a cartoon image of what we might see under the ground. All the blue area would be water. When we put in a drinking water well, we want more blue than we want brown, because that means the water is going to move the quickest, it's going to be most readily extracted. And it also means when contaminants get into it, there's going to be some dilution that occurs. So one of the things that we've seen at the two sites that we're talking about is we're seeing concentrations are increasing when you get into these non-porous, non-permeable areas, and as you move into the areas with more saturation, more water, you're actually seeing lower concentrations. So, moving right along, between 2013 and 2015 is when we gained most of our understanding about 1,4-dioxane, where it was coming from, how it was moving around, and what some of these concentrations were. And if I can grab my pointer, which one is it, Kim?
It's the one right
Upper.
in the middle.
Okay.
Yep, right smack in the middle. There you
Just to give everyone a quick idea, this dark black line is the Acton Concord Town line. We have production wells here and here. We also have production wells 1, 2, and 3 up here, our School Street well field. The purple areas that you see as of 2015, these represented areas where we kind of defined what we thought might be a 1,4-dioxane plume. As you can see, there's a lot of gaps in between those purple areas. So one thing that we wanted to do was better understand what was in those gap areas. Then you see a kind of hot pink color over here. This was the early stages of understanding how the nuclear metal site, which is right here in Concord, was impacting our acid production wells. A neat feature to realize here, there's a dark line. There's a dark line right through here. This is the Assabet River. And I talked about hydraulic boundaries earlier. For the better part of 40 years, most hydrogeologists that worked on these projects felt that the Assabet River was in fact a hydraulic boundary. And our protection zones around our wells actually reflected that as well. Well, what we found out was, and I'll get into why this is later, we actually were seeing that wasn't acting as a hydraulic boundary, and in fact groundwater was moving under the river towards our wells. I'll just note up here in this photo, it's not just taking up space, it's highlighting an older well that had been installed for the W.R. Grace investigation, and then this cone over here represents a well that's about 8 feet away, representing basically a redundant well that the folks working on the nuclear metals site needed to drill because they needed better information than we had from 40 years ago. So although a lot of people think hydrogeology is static, there's a lot of new information that can be gained and offer insight to us all. So talking about Grace, that was our initial concern, was the W.R. Grace site. We didn't know prior to 2013 that we had a second source. And they had been doing their groundwater sampling. In 2011, they were getting ready to put in a treatment system to treat the water they were extracting from down gradient, so downstream of the landfill that they had on site. And one of the things that they needed to do was extract that water and discharge it. Well, at the time, there was this cleanup goal of 3 that I mentioned, and one of the questions was, well, if we're not getting concentrations above that, do we really need to treat for it? The predecessor to Green Acton, ACES, Acton Citizens for Environmental Safety, thank you, it's been a while since I've used that acronym, really advocated hard to get EPA to require Grace to put in some sort of system. They ultimately did. That's the system pictured here. It's called the PhotoCat system. And that system really hasn't worked very well from day one, and we'll talk about that in a little while. Next, we moved to the northeast area. For many, many years, we didn't believe that there were any plumes going to the north. Eventually, in the late 80s, we realized that contaminants were moving to the north from the Grace site, and we needed to put in a system to remove the chlorinated solvents. Again, the 1,4-dioxane is coming from the chlorinated solvents that we've been looking at all along. We've been treating for them, we've been looking at them, and we've been trying to reduce that. So one of the things that happened was the system started pumping, and it started to extract higher concentrations of 1,4-dioxane out of the bedrock and discharging it closer to our wells. That was a problem for us. The town of Acton actually filed suit, and their case against Grace was thrown out, unfortunately. But it really got into this notion of how are we really protecting our wells. So very quickly, this is what we call a cross-section. Pre-1984, the primary contaminant at Grace was something called VDC, vanillidine chloride. And you can see back in technology times, we only had black and white, so the dark black here represents high concentrations. One of the things that happened was these contaminants sank from where they were deposited, and then they moved around, got into the bedrock, moved through the bedrock, and you can see here they're starting to come up into the vicinity of our Assabet wells. Well, here we flash forward to 1997. A lot of that's gone, but the 1,4-dioxane is still there, presumably, because that would have been commingled in that plume. One of the things that's happening now, I go back to my photocat that I was just telling you about, that treatment system that wasn't working so well. They're discharging that into what's known as sinking pond. Sinking pond then discharges into the water table here and makes its way back to our Assabet wells. So they're treating something partially, but then again reintroducing it and causing concern for the district. Here we see another cross-section. This is going north. Again, I mentioned mid-1980s to late 1980s. We didn't believe that there were contaminants going to the north from the Grace site. This illustrates that we are, in fact. So this is about where the manufacturing site was. The commuter rail track is right here. You go up, this is Losbrook Road, and then our production wells are here, and then Route 2 would be over here. That treatment system that I mentioned earlier that was started in 2011, they were extracting water right about here at MW6. So they were pulling these contaminants out. The orange is the high concentration, so they were pulling that up. They didn't realize they were going to find dioxane in it, and then they started discharging it up here, so it was quickly making its way down towards our production wells. So very quickly, UCMR 3, unregulated contaminant monitoring rule number 3. This is something that's required by the Safe Drinking Water Act. It's how EPA evaluates the need to regulate new contaminants over time. We expected to find it in our water system because we had already been sampling for it. And the reason that I'm talking about it is because it doesn't tell us where it's coming from, but it told us something about where 1,4-dioxane wasn't coming from in our community. One of the things that I think one of the other speakers will talk about, although it's found in industrial chemicals and commingled with volatile organics, it can also be in wastewater discharges. It's in a lot of consumer care products. And we did have some concern that there could be a source coming from septic systems and other waste discharges. This UCMR 3 program pretty much verified for us that that was not a concern here in Acton, even though we discharge all of our wastewater to the ground. So that's why I'm mentioning this here. Next, the nuclear metal site. In about 2013, I got a phone call from a hydrogeologist that was working on the nuclear metal site, and he asked if we knew anything about 1,4-dioxane, and I think I surprised him when I said, yes, actually, we do know something about it. And really, we were concerned for a couple reasons. One, the site wasn't located in Acton. There was this issue of the Assabet River, was it a hydraulic barrier? And one of the good things that came out of this was EPA was very receptive to our concerns. And ultimately, they set an improved cleanup goal that exceeded what was being required of Grace, but then they further improved that as we discuss things. So in the fall of 2015, this is roughly what the nuclear metal site thought their 1,4-dioxane plume looked like. There's basically a pink dotted line here. Our production well is here, Assabet River, and the old manufacturing facility up here. Next, we move forward thanks to an infusion of money from Mass DEP. There was about $1 million that was made available to better understand what was going on here, and we're very grateful that Mass DEP was able to use some of that funding and get a much better understanding of what was going on here. So just a year later, we had drilled, or the team had drilled a number of new wells, and we started to better understand where that contaminant plume was. Some of these high concentrations that you see right in the middle here, some of that has to do with the porosity of the subsurface material. So one of the things that is starting to become evident is that as you get into tighter materials, that contaminant might be building up more. So one of the things that people note is, well, there's really high concentrations here, and that's not very far from your well. And our well is pulling a lot of clean water from the north here and mixing it with some of the higher concentrations, and that's actually creating a natural buffer to some of these higher contaminant levels that we've seen in close proximity to our production wells. So this is a cross-section of what we just saw, going the opposite direction. So back here is the conquered side of things, and the plume comes down into both the bedrock and the unconsolidated overburden. That's where we're pulling our water from. And then our production well is here. The reason I'm showing this is because the Assabet River, I believe, is right in here. And there's all this other water between the river and where the contaminant is. And we believe that broad amount of saturated thickness is really helping to enable the groundwater to move under the river and not discharge to the river, which was the common thinking. This is just another view of it. It's a very narrow plume. And then finally, because I know I'm over, I promised that it would be 12 minutes, we'll talk a little bit about the concentration. I'm going to call it effluent because that's what's leaving. Someone said, you shouldn't use the word effluent. This is drinking water. So this is our drinking water concentration. The red line up at the top of the screen here, this is the Massachusetts DEP guideline of 0.3, which Diane, I believe, will give you better insight on. These are our concentrations. We are currently testing this on a quarterly basis. And to determine compliance with this guideline, to determine what, if anything, we need to do, we take a running annual average. So we take the prior 4 quarters, we average those, and we determine where we are. So as of the 3rd quarter of 2018, we're at 0.2. Just as a note, most lab detection is believed to be accurate to about 0.2. So we think we're pretty confident that number's real, and it gives us a pretty good buffer from where we are up here. And as Dan and Diane talk, you'll get more perspective, and you'll start to understand why we're seeing a drop in concentration here. So I am going to turn it over, and I hope there's good questions later.
There will be. Thank you very much, Matt.
And it's always tough being the first speaker.
It is, that is true.
Or the last.
Or the
Or the
last.
last.
Or the one before
The
lunch.
middle, I think.
They're all tough. All these topics are tough. So our next speaker, we're going to now hear about the health effects and how that 0.3 number was derived. So here you go, Diane.
Okay, hopefully you can hear me. I don't have a very loud voice. So, my name is Diane Genaro. I'm a risk assessor at the Mass DEP Office of Research and Standards. My background is I have a bachelor's in biology from Tufts University and a master's in public health from the Boston University School of Public Health. Am I loud enough?
Yep. Can you hear in the back? No.
No, okay, this is going to be fun. No,
The mic actually
mic
has-
The mic
work.
doesn't
Mic
project
doesn't
in this
work.
room
Okay,
like it's only
let
going
me
for
see if I
TV.
can shout.
Diane, would you like to go stand by that mic? Would you be able to speak louder from there? Or are you good where you are?
I'm fine.
Okay.
Yeah.
So,
Yeah.
The mics are provided by ActonTV, and they only go to ActonTV. They don't
Yeah,
project in
sorry
this
about
room.
that. It'll be clear
So-
audio in the recording.
If, all right, I'll try speaking more loudly. Do you hear me now? Okay, let's see how long that lasts. Okay, so anyways, I'm going to give you, this is an overview of my presentation. I'm going to give you the description of the difference between the Massachusetts drinking water standards and the drinking water guidelines, and then provide an overview of the process that we in the Office of Research and Standards, ORS for short, the process that we use to derive our Office of Research and Standards guidelines. And then talk more specifically about 1,4-dioxane, the health effects that we're familiar with, as well as the basis of the ORS guideline, or ORSG, for 1,4-dioxane. So some of you may be familiar with the list of drinking water standards and guidelines that is posted on our DEP website. The standards in this case are the EPA. It's a federal EPA maximum contaminant levels, or MCLs. The EPA derives the MCLs in a two-step process, with the first part being the identification of a health-based goal. And then in the second step, it considers other factors, including detection capability, treatment, and cost in setting the final MCL value. The MCLs for cancer-causing chemicals, called carcinogens, are set at about an excess lifetime cancer risk of 1 in 1 million to 1 in 100,000. And let me just define for you what excess lifetime cancer risk is, ELCR. Basically, what it is, it's a probability of getting cancer in a lifetime. So, for example, if you had an MCL set at a 1 in a million excess lifetime cancer risk, and you had that concentration, the MCL concentration in drinking water, and 1 million people drank that water, then you would have up to one person, because it's conservatively derived or protectively derived, might get cancer. So one person out of that million might get cancer. So MCLs are enforceable standards. And of course, they're set by EPA and they're adopted by the individual states, such as in Massachusetts. There is no EPA MCL for 1,4-dioxane. And now the guidelines from our list of drinking water standards and guidelines are the Office of Research and Standards, or ORS guidelines, ORSGs. And these are health-based target levels. The derivation of the health-based level is similar to the process that EPA uses to set their MCLs. The difference is that these ORSGs do not consider cost or other factors. ORSGs for carcinogens are set at an excess lifetime cancer risk of 1 in 1 million. And I just want to note that ORSGs are not enforceable standards. They're guidelines. But an exceedance of an ORSG triggers a source-specific risk assessment to be done by the Office of Research and Standards, with actions on that water system to be determined by the Drinking Water Program based on the results of that assessment. So the ORSGs are health-based guidance concentrations in drinking water. At the ORSG, significant adverse health effects are not expected, and they are based on drinking 2 liters per day of water for a lifetime. They're protective of sensitive populations. They're derived using both EPA Office of Water risk assessment methods, as well as EPA toxicity information when available. And of course, they apply to public drinking waters in Massachusetts. Now, in the derivation of the ORSG, both non-cancer and cancer effects are evaluated. So the toxicity information that goes into deriving the ORSGs is derived from animal toxicology studies, mostly, occasionally human epidemiological studies, but not that commonly. Separate toxicity values are derived based on non-cancer effects and cancer effects. And then, using the toxicity values, separate ORSG drinking water concentrations are set for non-cancer and cancer. The final ORSG is the numerically lower of those two ORSG concentrations, as you'll see. So just some additional information on toxicity values. The toxicity value for non-cancer is called the reference dose. This is the kind of the official EPA definition, but essentially what it is, it's an amount of a chemical that you can take in every day for a lifetime and not expect to get adverse non-cancer health effects. Then the cancer toxicity value that we use in deriving the ORSG is the unit risk. And the definition is here, the excess lifetime cancer risk associated with ingesting 2 liters per day of drinking water containing 1 microgram per liter of a chemical for a lifetime. So where do these toxicity values come from? Well, the EPA has a database online where it publishes toxicity values for a lot of chemicals, but not all chemicals. In the absence of the EPA information, the Office of Research and Standards will often go to toxicity values developed from other state, federal, or international toxicology programs. And in the absence of that, ORS has to go back to the dose response information from the primary toxicological literature, mostly animal toxicology studies, and derive their own toxicity values. And now, as far as the derivation of the toxicity values, these are, whether it's EPA or DEP or whoever that derives them, the process is pretty much the same. It involves a search of the toxicological literature for chemical information. And this is generally, for the most part, animal toxicology studies in which animals have been exposed to high concentrations of a chemical, and then the effects or the responses to those doses are noted, and that's known as dose response information. The studies are then reviewed, and the dose response information is evaluated. And then the study with the most sensitive effect in the most sensitive species is identified. And that's what that means. It's the study at which you see an effect at the lowest level. And then that dose at which there are no or very low effects is identified. And that's kind of the starting point for deriving toxicity values. So to derive a non-cancer toxicity value, essentially it's the reference dose. Essentially what you have is a no effect level in an animal study. And then you take that and then you further reduce it by applying a series of uncertainty factors. And these account for sensitive populations and differences between animals and humans. To derive a cancer toxicity value, it's a little bit more complicated. The cancer endpoint is evaluated slightly differently than the non-cancer. It's derived in terms of risk. So animals in animal studies are given high doses of chemicals. And this is to magnify any possible effect. But in the environment, the concentrations that you see in the environment are a lot lower than what you would see in an animal study. So there's basically an extrapolation step to estimate. What you're estimating is the probability of getting cancer at the low doses. If you see the little square there, that's the area of interest, as opposed to the little stars, which are the dose response information from the animal study. So that information that you're looking for is basically the change in the number of tumors as the dose increases at low doses. So that's called the cancer potency factor, and that's identified from the dose response information. And then that cancer potency factor is then used to estimate the unit risk that I had described earlier. So let me just get into some 1,4-dioxane specific information. So regarding health effects, first of all, as with any chemical, whether you get health effects depends on, of course, how much of a chemical you have in the water, the amount of water you consume, and for how long you consume it. As toxicologists say, the dose makes the poison. So the liver is kind of the target organ of concern for 1,4-dioxane. 1,4-dioxane given to lab rodents at high concentrations in drinking water over long periods of time caused adverse liver and kidney effects, and those are the non-cancer effects, as well as liver and nasal cancers. Based on animal studies, the US EPA determined that 1,4-dioxane is likely to cause cancer in humans. And then as far as human data, there were 3 studies in which workers were exposed to 1,4-dioxane at work for many years and did not have a greater number of cancers than non-workers. But the studies were not really strong enough to rule out some degree of risk. So to calculate the ORSG, the numerically lower of the assessment done for non-cancer and cancer are compared, and the numerically lower of the two is selected as the ORSG value. So the non-cancer toxicity value for 1,4-dioxane is a reference dose of 0.03. Those are the units, milligram per kilogram body weight per day. This was derived by US EPA in 2010 based on a 2-year chronic drinking water study in the most sensitive species identified, which was the rat, and the critical effect was on the liver and kidneys. Based on that information and the toxicity, on the toxicity value, a ORSG, drinking water concentration, was derived of 210 micrograms per liter. And again, that's based on drinking 2 liters per day of water for a lifetime. I'm not going to go into too much detail about how this was derived, because as you'll see, the cancer risk drives the process for 1,4-dioxane. However, if you have questions, I'll be glad to answer them later on, given our time limits. The 1,4-dioxane cancer toxicity value that we use to derive the cancer-based toxicity value is the unit risk value of 2.9 times 10 to the minus 6 per 1 microgram per liter. And that, again, was derived by EPA in 2013 based on a 2-year chronic drinking water study in the most sensitive species identified, which was the mouse, and the critical effect was liver tumors. As I mentioned, the cancer-based ORSGs are set to 1 in a million excess lifetime cancer risk. So to determine the ORSG based on cancer effects, you basically you divide the excess lifetime cancer risk by the unit risk, and we have a value of 0.3 micrograms per liter. And as you can see here, the lower of the non-cancer and the cancer-based ORSG values is the cancer-based one of 0.3 micrograms per liter, and that is what the ORSG for 1,4-dioxane is. And to summarize, the 1,4-dioxane ORSG is 0.3 micrograms per liter. It's set at a level in water that would not result in an excess lifetime cancer risk of more than 1 in 1 million if you drink 2 liters per day, every day, of water for a lifetime. It's protective against non-cancer, possible non-cancer effects, as well as cancer effects. It's not an enforceable standard, but an exceedance triggers a source-specific risk assessment be done by the Mass DEP Office of Research and Standards. And it's purposely set 10 times lower than the drinking water program's risk limit of 1 in 100,000. And that's the risk limit that they use to assess long-term use of drinking water. And the reason for that is that we consider the possibility that other carcinogens might be present in the water. So they are purposely set 10 times lower than the risk limit that the drinking water program uses. And that's a very quick summary. I hope you heard some of it. And this is my contact information. Feel free to contact.
Thank you so much.
Okay.
That was, Diane, that's the part of the whole situation that I understand the least, so I am extremely grateful to you for coming to share this with us. So our final expert this afternoon is going to talk about what's being done. Vann.
Wow, this is just walking up here. So I'm an engineer. I'm both a chemical and environmental engineer. I went to school with him and I worked with him. My expertise is, I've got sort of expertise in two main areas. One is sort of the fate and transport of chemicals when they get in the environment. So if you've got dioxin, it gets into the ground, what happens to it? And then the corollary to that is, what can we do to get it out of the ground or get it out of the water? So my expertise is in both of those. So tonight I'm going to talk about a little bit more about how 1,4-dioxane is getting into our wells, working with what Matt had to say before, what you can do to get it out of our wells or keep it out of our wells, and what happens to water when it gets pumped out of the. So the way we're doing it in town, for dioxin, it's a problematic compound. I'll talk about that a little bit. And the best way to keep it out of the wells is to intercept it before it gets into the wells, and that's to pump it out of the ground. And once we do that, we have to do something else with it. So I'll talk about that. What happens to it when we take it out of the ground?
Can you try speaking a little louder?
And I will try speaking a little louder. So here's a little bit of information about 1,4-dioxane that comes from that great technical fact sheet that's listed up there. So the EPA has done, so I should have said this before. For many years I was a consultant working in town and nearby. And for the last 7 years I've worked for you guys, for the U.S. Army Corps of Engineers. So I've never worked for the EPA, but I'm going to endorse the EPA right now and say that they have if you really want to know more about dioxin, they have a easily found technical fact sheet about 1,4-dioxane, really thorough, well-written. Not everything the EPA does is really thorough and well-written, but this is. Is anybody here from the EPA? Okay, good. So this is an idealized version of what you have when you have a pumping well. So we have these wells in town that are pulling water out of the ground. Some of us have private wells that are pulling water out of the town, or in New England, about a quarter of the water comes out of private wells. Our water here mostly comes out of big production wells that produce a lot of water. And when you pump a well like that, water comes from the sides, and you have a cone of depression, and you've got you can see that water will come from near the different distances from the wells. So the more permeable the material is, like this gravel, you get more water coming from closer. So this is just sort of a short arrow, and from the less permeable stuff, you get less water, but it comes from farther away. Interestingly.
There's a pointer up there if you want to.
Yeah, this is
Okay,
good for
you're
now.
doing okay.
Thanks. So this is the ideal of what a pumping well does. And this is looking at that map of looking down on Acton from above. Now I will use this. Nuclear metals is over here where they release some 1,4-dioxane, and we have a well over here. That's Acibet 1. That's a production well. And there's an area around that we expect that's called a wellhead protection zone. And that's 400 feet in diameter, so this is 400 feet, in radius, that's 400 feet. And that's where you assume that most of the water is coming from when you pump the well. Now there's a plume that's coming underneath the river, and it gets near there, and some of it gets to this zone, and once it gets there, it can get pulled into the well, and that's what's been happening over the last some number of years. So what do we do about that? We can either try to destroy the contaminant or in the ground, which is very difficult to do for 1,4-dioxane. That's a very stable compound. It can't be destroyed by most methods that we have in the ground. Or you can pull it out of the ground and treat the drinking water before you send it off to the residents. Or you can intercept it, and that's what we're doing. That's our selection. That's what, and the reason why that's our selection, there's two reasons that's our selection. One is that's probably the best way to go, and the other is this dioxane that we're right now near Acebet 1 is the problem of a Superfund site that's across the river. The people who are responsible for that Superfund site are responsible for that dioxane. So they are being asked, they are being demanded, there's a demand by the EPA that they do something about the dioxane. The best thing they can do is intercept it before it gets to our well. They intercept it and they treat it, and I'll talk about that in a second. So this is a schematic of, a plume. You intercept the water. Here's our pumping well. Eventually, our pumping well is safe because we're intercepting the plume. For here at Acebet 1, so here, this is Acebet 1, here's their clone depression. There's an extraction well that the nuclear metals responsible parties have installed right there, EW1, and it is up gradient and outside of this zone that where most of the water is coming from, and the intent. So before that well was installed, this is the plume. The plume gets to our well. Now that it's installed, the intent of the approach is to intercept it. The water that's down gradient, that's between the extraction well and our production well, that's going to keep flowing towards our well for a period of time, and then this will clean up over time. So that's the plan, and right now that appears to be what's happening. So they started pumping this well maybe a year ago, roughly, sorry about that. So these are the contours. So the way to read this, there's two sets of contours on here. One are these blue contours, which is the water level in the ground, and water flows from the highest point in the water level to the lowest point in the road. Water flows, as we like to say, downhill. So this water level is higher than this water level, it's higher than this water level. So this is the direction the water is flowing. Over here by the well, there's a much steeper draw, that's that drawdown curve, that's that cone of depression. So it looks much steeper. This water is flowing from here into our production well. Well, right here is our extraction well, and there's these pink contours, and those are the concentrations of dioxane in the ground, and the largest concentrations are here, and it looks as if there's a gap starting to open up right here. This black line is the estimated line of where the capture of the groundwater is in this extraction well. So they're pumping this extraction well. Water from up here is flowing toward it. Water from down gradient between the two wells. This extraction well can sort of reach down gradient and pull some of this water back, sort of. Everything that's down gradient of this line, that's this side of this line, will keep flowing towards the well. And that's the way it's working. One of the things that you saw in Matt's last slide earlier was that the concentrations over time have been going down in the drinking water that's going out into the system, and that's likely because they've started to intercept the plume before it gets to the wells. So what do they do to the groundwater that they pull out of the ground. So people have asked that question before at other meetings that I've been at. They, in the last year, while they've been trying to figure out the best thing to do, they've been taking the water and they've been pumping it through activated carbon, liquid, through a carbon filter. And maybe you're familiar with carbon filters from people put them in their drinking in their homes all the time. They take out odor, they take out taste, and they take out organic chemicals. They're not very good at taking out dioxane, but they're doing a reasonable job of it. They take that water that goes through the carbon, and then they discharge it to the acid bed river. In the meantime, they've been testing another process for permanent application out here. Maybe that's good enough for that. So far they've been removing about 45% of the dioxin that comes out of the ground, in the carbon, and then they discharge the rest to the river. The EPA has required Nuclear Metals Organization to eventually treat the groundwater to a level of 0.46 micrograms per liter. So that's the EPA's number. It's not the same as the DEP's number, but they think that that's protective. So they've been testing another approach called UV advanced oxidation. When they've been pilot testing that, and they've managed to find a way to implement that so that it's essentially coming out as non-detect. So it goes into these reactors. They put in the reactor some oxidant, they shine some UV light on it, and they are able to destroy the dioxane in the reactor. So the water coming out of the extraction well, EW1, is around a little bit more than 10 micrograms per liter, and it's getting treated down to less than 0.15, less than the detection limit. That's what a reactor looks like. So right now, there is a building being built over by the skating rink. No, I'm not sure exactly.
Behind Stop and Shop.
Behind Stop and Shop. And there's a bunch of equipment that's being stored over there. And they're relatively soon going to install 6 reactors that look like that and treat all the water that comes out of EW1 for $6 million, and then hopefully our well will continue to get clean. I'm an Acton resident, did I say that? So in addition to this, there's the question of, well, for how long are they going to pump that well, and what's the story? I mean, is that going to always work? What about the dioxane that's upgrading to that well, that's slowly making its way? So that dioxane will take a very long time to get to EW1. So the EPA is requiring Nuclear Metals to go and try to remediate the source of that dioxane. So far, as they know, there's some dioxane in the bedrock over at the Nuclear Metals site, where they've been doing a lot of removal of nuclear wastes, right, of buildings that are irradiated. They found up to around 100 micrograms per liter in the bedrock, and eventually they have to get that out. They've got a couple of options for doing that. One is to put in more wells over there and pump it out. It's much harder to pump it out of bedrock than it is out of the sand that we have our wells in. But they might try that, or they might try to go and oxidize it in ground, add a chemical reactant called sulfate, and try to destroy the dioxane in the ground. That is to be determined. And I know people have asked some questions before about biodegradation. Dioxane is this unusual compound that, when it gets in the ground, it moves very quickly, faster than all the other compounds that we usually deal with. It doesn't sorb to things, so you can't remove it by carbon very easily. That's why they can only get 45% of it out with carbon, whereas the other compounds that we have to deal with usually all come out very quickly and very thoroughly. and it doesn't biodegrade, although there are some bacteria that people have been finding recently that appear to treat it, but not at our concentrations, only at much higher concentrations. And I'd be happy to answer questions. That's all I have to say.
Okay, thank you very much, Dan.
Sure.
That's great. So we're moving on to the Q&A part of our evening now. Let's see. So we have a few ground rules for how to do the questions. I'm going to ask you to come down to the microphone when you speak. However, as we learned earlier, the microphone is is only going to ActonTV, so please try and project your voice loudly. Secondly, state your name. And then after that, we're here to learn tonight. So we have this amazing opportunity of these three experts who are here to share their knowledge and their insights with us. So I'm asking, please, people step to the microphone and ask a question, and don't use your time at the microphone for opinions or policy statements. Just ask your question. And then finally, please only ask one question, so that there's a lot of people here tonight, and if you've got more questions, you can go to the back of the line. And then finally, let me just say that I don't know what you guys are going to ask, but I'm pretty sure that there will be some questions to which there are no answers. One thing I learned in a whole lifetime of studying earth science is that what we don't know about how the earth works is vast, and so there will probably be questions that nobody knows the answer to, and that's just the way it's going to be. All of the speakers have offered to be available for additional questions in case more questions occur to you after this evening. And in addition, the head of the office of that Diane works in, the Office of Research and Standards, Mark Smith, has offered to be available for questions. And also our remediation manager for our two local Superfund sites, Chris Smith, of the EPA, is also available for questions. So you can write to those people if you think of more questions. So who would like to ask a question? The microphone is open.
I'll ask a question.
Okay, please.
I'm Mary.
Stand at the microphone, please.
I'm Mary Lynn Miller, and I found this very interesting and reassuring, actually. And I followed, water contamination through the years, and I'm a retired physician, so it pops up in medical journals. And often the Superfund sites that I used to read about were discovered by, incident clusters of leukemia, or clusters of something else. So this is very reassuring that.
Mary Lynn, what's your question?
Well, so so the first question was 1,4, I'll ask it of Ms. Genaro, was 1,4-dioxin picked initially because of the company it keeps, meaning that it's, I've been told, a degradation project of certain solvents, or how did they decide to feed that to rats, I guess is what I'm saying. Do you know? You may not know.
I don't know. We've had a guidance value for 1,4-dioxane for a number of years. So it probably predated, this situation. And probably at the time there was a need for toxicology information, and that's probably, the impetus for, I'm guessing.
So, no clusters that you know about in humans.
Yeah, I don't know of any. And that's typically something that the Department of Public Health usually investigates. It's not something the DEP does, but I'm not aware of any.
Thank you.
Thank you.
Can I just add to that?
Sure.
So 1,4-dioxane is this funny compound that was added. It was added specifically to actually a very specific chlorinated solvent, 1,1,1-trichloroethane, which we've probably all used at one time or another as a spot remover or something crazy like that. It was added to the, it's not a degradation product. It was added to stabilize that, to keep it from reacting with things that you would put the solvent in. So they add small amount to that. So 1,1,1 trichloroethane was the primary actor for this. You would have a lot of 1,1,1 trichloroethane and a little bit of dioxane, but it also, it's found in some of the other solvents, the solvents that W.R. Grace had, or the solvents that NMI had, but it's not a degradation product event. I mean, it's very specifically targeted for use in that way.
Thank you.
Hi, Ginger Harris, West Acton.
The mic doesn't project into
Yeah.
the room. The mic only goes to the television, but I'll repeat the question if it
Okay.
seems faint. Yeah.
I'm new in Massachusetts. I wanted to know if anybody drinks, or you expect anybody to be drinking in the future, water from the Assabet River downstream from this location. And is W.R. Grace and Nuclear Metals, are they in the same site? The same location?
So I'll just repeat the question a little bit louder if you don't mind. So the question is, do you expect anybody to be drinking the water from the Assabet River downstream from this site?
So I'll address that. The town of Billerica currently withdraws their water from the Concord River, which the Assabet River flows into. The town of Billerica, just like we were required to do this UCMR3 program, Billerica was required to do that, and I believe they did not have any detection. So one of the things with 1,4-dioxane is dilution really does have a large impact on the concentration. So up gradient of these sites in the Assabet River, there is a very low level concentration, I believe around 0.1 is the current kind of ambient concentration. And based on what we're told, that's really getting diluted down as it approaches Billerica. And the second question...
Actually, if
Only
you
one
put up,
question
there's
per
a,
person.
oh,
Yeah.
Yeah, one of
Go
and the second question about
Yeah.
are they the same site? It might help to put my presentation up.
Yeah.
So the quick answer is no. They're not at the same site. They have two kind of separate source areas. Slide 6.
Six.
But one of the things that you see is they're kind of converging together down here where the river is.
this is Nuclear Metals.
Yeah, so Nuclear Metals is here. Our production wells are up here. So the two sites kind of converge in this area.
Where's W.R. Grace?
And then W.R. Grace is the old manufacturing facility is where the A is. Right in that area. The landfill is just down and to the right. So, you know, they're in close proximity to one another. Obviously, their aquifers have some potential overlap, but they do have two distinct, or more than two distinct source areas.
Okay. John?
Dr. John Blute. The studies done on rodents were done, as I think I saw in my limited review, were done more than 40 years ago. Have there been any other updated studies that I'm not familiar with or we're discussing done on either the toxicology or the potential carcinogenic effects of this substance?
I believe that, let me see. The critical study that was used as the basis for the unit risk, you know, and cancer drives, you know, the process for the ORSG, was developed in 2009. Was
So that's the
conducted.
primary studies, 2009?
Yes.
The
that was-
1974 study?
I think that was one of the supporting studies. I mean, there's a number of supporting studies that they looked at. But I mean, they all pretty much point to, you know, the main target organs are liver and kidney.
Right.
And they review a bunch of studies. The EPA reviews a bunch of studies in the review that they do systematically. And then they choose one, and this one, this Kano et al. 2009, was the study that was used. You know, there's a lot of information, if you're interested in going
Yes.
into it in more detail, there's a lot of information both online, and then if you're interested, we can, you can contact me and I can put you in touch with one of our toxicologists and they can talk to you about it. We're glad to talk to you.
Contact information
Yeah.
there, but
That's great.
as you're well familiar with medical science, things are evolving and they're evolving reasonably rapidly. And it'd be interesting to see what happens because, as you're well aware, this particular substance is commonly found in very small amounts in many products, everyday products, not just this area that we're struggling with, but in many products, shampoo, I mean, it was extraordinary when I started to get into this, but I think it's important to understand what is the science
John, it
telling
would be
us.
really helpful if you were to get in touch with their toxicologist, and John is on the water committee as well, and bring that
Yeah.
information back to our committee.
Definitely,
If you were willing to research that some more, that would be a great service to the
yeah,
town.
we'll gladly,
Thank you.
Yeah.
follow up with that.
So
Next.
for what it's worth, though, I just looked it up, and it is a primary study. It's not referencing that, it's not a regurgitation of an earlier study.
Well, I think that's good.
2009.
It's good information. It's still, 9-10 years old. Still, so follow-up studies are certainly indicated in many areas of medical science. A lot of effort and time and money are being spent on this particular area.
Thank you.
I'll be in touch.
Okay, that sounds good.
Hi, my name is Alexandra Suri, and I was wondering, as more people now are trying to eat local, whether there is any contamination that you would notice in the fields, and like the vegetables, and other things, whether any of it travels through groundwater and is absorbed then in the plants, or if anybody has looked at that.
That's not something, let me see. That's not part of this evaluation, so I can't tell you for, one for dioxane, I'm not so sure whether that would be, usually we do, studies like that, or we have some information on metals, but as far as 1,4-dioxane, I am not sure. But once again, I can go back to my office and see there is one person that deals with plant uptake, and I can contact him and get back to you. My inclination is to say that it's probably not taken up by plants, but that's just a guess. So I'm going
It's
to.
a really good question.
But I was wondering, when you looked at the water movement, whether there is actually any agricultural land above it where you've noticed a lot of contamination,
Sure.
Because it could occur to me, I try to buy so much organic, right? But if the contamination is coming from underground, I have no control over it, so it's almost pointless, if I'm really, trying to pay attention to all of that, and my plants are, my vegetables are getting,
That is a really good question.
So
I don't-
locally,
Yeah, that is a good point.
as
Yeah.
part of the site investigations, that specifically has not been looked at. When we're talking about the groundwater here, and at the closest, it might be 10 or 15 feet below grade, and anywhere up to 40 or 50 feet below the ground surface. So for vegetables, I wouldn't think there'd be direct uptake. I can tell you, outside of the Acton area, on a national level, it has been found in different forms of produce: tomatoes, lettuce, coffee beans, and milk. So at some point, it is getting into the food stream, and that may be because they're using contaminated water to irrigate or produce feed crops for cattle. So that is a potential.
So the
that's-
dioxane coming from nuclear metals is not, that's not getting into anybody's produce in the groundwater, because that's all much deeper than
Yeah,
produce.
I put the diagram up, and you can see again how much below the surface it is. But the irrigation water,
I can see what I can find out.
go ahead, that would be
Yeah.
wonderful if you could
Okay.
find out about that for us, because I haven't heard that question raised before. Norm?
Hi, my name is Norm Strolli. Just a thought, if we get an answer like that, could we put it on the Green Acton website maybe?
Totally, the Green Acton website has been deluged with dioxane information recently, and any new information that comes forth out of this evening or in the follow-up correspondence, we can certainly put on the Green Acton website.
I noticed Matt brought his own water.
I did, in an Acton Water District bottle. Full disclosure, I no longer live in Acton. I used to live directly adjacent to the Grace site. This is a hybrid. I top my water bottle off, so it has about 85% Acton water and about 15%, well, maybe 10% from my private well, and the rest we won't get into what 5%. But I personally drink the Acton water.
Was that your question?
No.
Daily.
Quick question, so if we're pulling water out our well, not the prevention well, but where we're drinking water from, does that help bring the plume to the water, or is it purely just the gravity going to bring it no matter whether we're sucking water out of the well or not? And if it does have an effect, if we pull less water out, would it mean less dioxane in the well area or more have no effect?
So I'm going to answer your second question first. We have seen that when we reduce the flow rate, we actually see concentrations go up. And this goes back to a couple things. One, at a higher extraction rate, you're pulling in more water from potentially further away, which means that presumably you're diluting some of that down. So that's something that we've kind of, I'll say anecdotally, seen, is that at lower flow rates we see higher concentrations. Relative to, I think you're saying, is our pumping dragging this plume? It's certainly a possibility. This aquifer wasn't studied until we were pumping groundwater out of it, and we've had discussions about what happens with pumping or not pumping. One of the benefits of pumping and having that known extraction point, it kind of gives some definition to the plume. So these things aren't just going to keep cruising outside of a given area, especially up in the School Street well area. We're basically containing that plume. We're saying, all right, it hits our well, and this plume doesn't continue to march to the north. And then certainly down in South Acton, again, having at the Assabet wells, having that extraction point possibly prevented that 1,4-dioxane plume from being really wide. So one slide that I cruised through very quickly, which I believe is the next one, shows kind of how narrow this nuclear metals plume is. Whereas with Grace, it's much more diffuse. It spreads over a much wider area, and we think that could be attributed to the fact that the wells don't have as direct of an impact on the groundwater there, so it can spread out more, which makes it, in my opinion, it makes it a more challenging thing to remediate, because you don't have this nice, well-defined plume.
For WR Grace, you don't have the well-defined.
Correct, yeah.
Okay, thank you.
Thanks.
I'm going to read a question that was emailed in before we start on second round of questions. So the question that came from a person who couldn't attend is, are there, and I think this is probably a Diane question, but if the others have things to say about it, I'd be interested to hear also. Are there other public water suppliers in Massachusetts who have exceeded the 0.3 micrograms per liter guidance, and if so, what happened?
As far as I know, there were a few others, and we initiated. We did do an evaluation of them. I'm not sure where that went. I haven't been following it. That's a drinking water program issue. So,
would you know, Matt?
Yeah. So yes, there have been. I actually didn't bring that slide with me. I've done a prior presentation where it identified who was above the ORSG and who was below. I want to say that it was about 30-something that were,
30 water suppliers?
Yeah, or water supplies, or wells, sorry.
Wells,
Or,
okay.
or sources. So it could have been
yeah.
a surface water intake, it
Yeah.
could have been a well. I want to say it was somewhere in the 30 range that were above that. Different suppliers have done vastly different things. Some have shut off a supply, some have gotten a different source of supply, some have treated it, some are blending it, some, you have things that aren't, these big production wells that we have, and they've gone and connected to, a public water system. So one thing that people don't always think about is, let's say you have a condominium complex that has their own well on site, that's actually considered a public water system. So someone like that who may have found 1,4-dioxane, they could then turn and connect to a larger supply like us. So that's kind of the general landscape of what folks have done. And some people have just done nothing and have effectively, kind of brushed it under the carpet and said, yeah, great, we have this information, and, they're effectively choosing not to, do anything more with that information.
Okay, back to the attendees.
Richard Kelleher. I have an odd question. I'm an architect, and I always thought dioxane came from the production of things like PVC roofing, but Dan, you didn't say anything. You said it's from, was it from the tetrachloroethylene or whatever, the cleaning compound?
Well, the primary place that I know of is from, as a stabilizer in chlorinated solvent. We could open up that EPA fact sheet. One thing, when people put together things with PVC, they often use PVC glue, and a lot of times that PVC glue uses a chlorinated solvent, and there can be dioxane in that. There's also something called tetrahydrofuran in there. I mean, there's different things that have been defined in PVC glue. I don't think it's found in PVC, but I could be wrong.
You might find it there.
Yeah, that's exactly right.
This is the place to go for your answer here, this fact sheet. So, thank you.
For all of the 1,4-dioxane in Acton, what percent of it do you suspect comes from either one of these manufacturers or from other sources, like the glue and so forth?
So we, the district, based on the information we have, believe the majority, if not all, of the dioxane that we see in our wells is coming from these two sites. So again, during this UCMR3 program, we sampled all 22 of our sources throughout Acton, and we did not see 1,4-dioxane in those, telling us that, broadly there isn't, this influx of it from other sources. Down in the area of our, South Acton wells, there are other historic industrial uses that has been heavily industrialized since the 1800s. Granted, they weren't using chlorinated solvents then, but there is a long history in that general area of industrial use. So right now, based on our knowledge, we believe those two Superfund sites are the contributors, but that doesn't preclude another source or sources being identified at a later date. But up until 2013, we believed at the time the only source was W.R. Grace. So certainly new information can change our thinking on that issue. I don't know if anyone else has any thoughts.
Well, just looking quickly at this EPA fact sheet, the primary source of it is from these chlorinated solvents. So it's used in other things in much lesser quantities. So.
Hi, my name's Corin Vickery, and I was wondering if you guys are aware of any co-contaminants from either of these sites, and if so, if there have been studies to evaluate whether they potentiate the effects, the health effects of the 1,4-dioxane.
Want me to? Okay. So both of these sites, the primary contaminant was not 1,4-dioxane. So at W.R. Grace, the primary contaminant for years was a chlorinated solvent, or a couple of chlorinated solvents. And those actually do have MCLs, maximum contaminant levels, limits from the EPA, and they have known health effects. The 1,4-dioxane is sort of a newcomer. And same thing for nuclear metals. The reason why there's any 1,4-dioxane there is because they use some chlorinated solvents at nuclear metals in their processes. But one of the things about 1,4-dioxane is when it gets in the ground, it travels at the speed of the groundwater. So groundwater actually goes from one place to another. It can travel hundreds of feet a year. It can travel thousands of feet a year, depending on where it is. Those other compounds move much slower. And they may never make it to, like the Acton water supply well, whereas dioxane will race ahead. And those other compounds actually they will naturally attenuate over time. The bacteria in the ground will act on them and they'll degrade them. And dioxane being very resistant to that, so it just keeps going. And so maybe that's enough.
Yeah, so, relative to the question, Dan is absolutely correct. 1,4-dioxane was not a primary contaminant of concern at these sites. The other contaminants we've known about for the better part of 40 years. I'm going to ask for a lifeline. 1982 is when we began treating the public water supply, is that correct? Thank you, Ron. So we've been treating these other chlorinated solvents since the early 1980s. So full disclosure, we have worked with DEP to go through a risk assessment, and the belief was that we didn't need to take into consideration other contaminants, that we could in fact look at 1,4-dioxane on its own, because we have been and continue to treat the other contaminants of concern here.
Am I allowed to make a question as a Concord resident?
Sure, it is an open meeting.
My name is Tim
answer?
Rose, live in Concord, and I've been a member of the Technical Advisory Committee for CREW, the Citizens for Environmental Watch at NMI, for more years than I care to remember, but it's back in the 80s. And one comment that I found rather both discouraging and amusing in some ways was we had no idea dioxane was going to be a problem up until we saw it and called you people, and it really would have been much better if we had had a little more communication between you people and our people, but that isn't always the way it works. I think the problem that he's having with the PVC, I am a chemist, by the way, or was a chemist before I retired. I think he's got dioxane and dioxin mixed up, because that does come from PVC when you essentially hydrolyze it or burn it.
When you burn PVC, yeah.
But that's not dioxane, it's dioxin, which is the real bad. Anyway, my question is, Dan, could you elaborate a little more on what is indicating that this extraction well that they're using has in fact split off or stopped the dioxane part that is moving towards the well? You showed a picture showing that it's split into two. How well is that being categorized, would be my question.
Well, so this is all new. They've only been pumping for 1 year. And environmental data is notoriously squirrely and not as consistent as you'd like. So you take a sample one day, you go back the next day, you might see something a little different, or you go back the next month, there's seasonal effects. But right now, if you were to take the data and contour it the way they've done, it does look as if these two contours are the same. This is 5, and this is 5, and
Yeah,
so
you had a blow up
this is mine.
where it showed up split much.
That was a schematic.
Oh, that was just a cartoon. This
one.
This one,
one
next
more
one.
time.
this one,
That
was a,
This is a cartoon. This is the intent. I should have underlined intent. So,
okay.
and this, for what it's worth, this has been shown many times in many places. that this can and does work.
And it is in fact going down, I mean, just,
So down here, it seems to be going down, yes. But
I do
1
just
year
wanna-
of data.
Yeah, I do want to put one caveat on that drop that you see.
Yeah.
You know, Dan, you know, would have led the group to believe that it was solely because of this pumping, but we're also seeing decreases in other sources. We have, you know, 5 wells that pump into that treatment facility in South Acton.
That's
So
in his-
Yeah, that's right.
we're seeing, you know, some. We're basically seeing stable concentrations at Assabet 1A, but we're seeing declines in some of the other wells. So you know, it's difficult to point and say, oh, the intervention is what's causing the decrease.
Yeah.
So
So
there are
this is-
multiple
this
things
is
at play here.
5 wells that feed into this, is that right?
Yeah,
5
this
wells,
is
okay.
5 wells, and keep in mind, back here, we're closer to that impact from the Northeast Area Treatment System that I mentioned. So Grace had been pulling the contaminated bedrock water out to get to the VOCs, which we can readily treat, and they were pulling that out, not treating the dioxane, and that was getting recharged to the overburden. And at that time, we were seeing an increase in our School Street wells, and we believe now that that bedrock extraction has ceased, that has finally, you know, kind of returned the School Street wells back to, you know, what their natural condition
And
might
this
have
includes
been.
the School Street well?
It does, yes.
I didn't realize that. Thank you. Sorry, then.
No problem. I mean to misspeak.
I'm trying to remember one of my many questions.
I could ask another question from the email while you think,
Okay.
Ginger.
Okay.
So an email question was, what is the value of reverse osmosis filters for removing 1,4-dioxane from drinking water?
You know, I should know the answer to that. I think that it's too small a molecule for reverse osmosis to be very effective.
I believe that's correct. I think it, similar to the carbon, it has some impact, but it isn't a, you know, surefire treatment methodology.
Right. So if somebody's thinking about using that on their house, maybe they have something like that on their house, and they're hoping that that's taking out the 1,4-dioxane. It might be helping a little, but it's probably not doing much.
Okay. Thank you. Okay, Ginger.
Well, let me ask one other. Someone mentioned a suit that was dismissed. Can you describe more about the suit and why it was dismissed?
I'm going to repeat the question a little louder, Ginger. So there was a mention of a suit that was by the town of Acton, I believe, that was dismissed, and the questioner is asking for more detail about what was the suit and why was it dismissed.
So, not being part of the town of Acton, I may not have every detail correct, but essentially, the town of Acton sued W.R. Grace because they were arguing that shutting down that Northeast Area Treatment System was not returning the groundwater to a usable state. So the town of Acton actually has a local bylaw that requires, you know, people that have contaminated the environment to return it to a usable state. The town's argument was, by shutting that system down, you did nothing to, you know, further reduce the VOC contamination there. And essentially, when that made it before a judge, he dismissed it, saying that the local bylaw could not, you know, supersede what the Superfund program was requiring. So they basically deferred to the fact that this was a federally regulated site, and that the local bylaw therefore did not have standing. That's my understanding of that suit.
Sounds right.
Thank you.
Hello again. My question was about just generally water, you know, quality. When I looked at the report, I think arsenic was very high, and there was some mention of trying to lower that, and I was wondering if that's coming from the ground, or is that in any way related to the Superfund sites? And also, I noticed that it said that pesticides are tested every 3 years, which I found a bit odd because glyphosate at least seems to be in pretty much everything, and so I thought it would be something more relevant, something that we should know on a sort of more regular basis than once every 3 years. I didn't think that, testing water should be that expensive, so just sort of wanted to hear your thoughts on that.
So I actually have a question for you. What report are you referencing, the arsenic?
I think it was Town of Acton, the one that it said, where you list all of the, sort of contaminants and all.
So on the arsenic issue, we have seen some in one of our supplies. We currently treat that with carbon filtration at that site, and that actually does a pretty decent job, even though that's not the preferred removal for arsenic. That arsenic is naturally occurring. Arsenic has been an issue on the WR Grace site, but we haven't seen that impact in our wells. So some of these chlorinated solvents, as they've interacted with the bedrock, that's actually mobilized arsenic that was naturally occurring to become more mobile. But the arsenic that you're referring to that's reported in our water quality report, as far as we know, is naturally occurring. It's on the western part of town. As you move west from Acton, you start to get into the arsenic belt of Massachusetts, which really is naturally driven. And there's a lot of great research that USGS and Mass DEP have done to understand the arsenic in those areas. Relative to the 3-year cycle for pesticides, our sampling is dictated by what do we think the risk is and have there been detections previously. So Mass DEP has a master sampling schedule, and it looks at historic water quality data, and it looks at actual land use risks or natural features that may drive the need to sample more frequently. But that is pretty much the standard, and we have not seen detects in any of our 3-year sampling.
So you haven't detected any glyphosate, because I couldn't really see anything in the
So could
report.
you, I'm sorry, I'm looking for one question per person, but please, I'll put the addresses back
Okay.
up. And also the Acton Water District Commissioners are open meetings, and so they are happy to hear questions.
And just so you know, our water quality report doesn't show everything we test for, it shows things that we detect. So we may do 1,000 tests, but we only report 30 things because we're only finding 30 things out of those 1,000 parameters that we look at.
And also, I'm not sure glyphosate is one of the is an analyte in a pesticide run. I just don't know. I wouldn't bet it is.
What's an analyte?
It's not one of the things that you analyze for.
Something you analyze for, okay. Okay.
I'm Jim Brockmeyer from Acton Center. I'd like to know, should I drink Acton water or should I buy the commercially available bottled water? In other words, how does Acton water compare to commercial bottled water?
And we were just talking about that.
Yes, we were. So the bottlers in Massachusetts are not required to test for 1,4-dioxane. So you don't know where that water comes from. I would drink Acton water because I know it's been tested.
Well, I would too, because my results were exactly the same when I tasted bottled water from Poland Springs and other places. Acton water is the best.
We're drinking it now.
I'm going to ask another question from the email list, and then we'll get to Ginger again. And so this is, I think this is another Diane question. So right now, 1,4-dioxane is a guideline with Mass DEP, and there is an enforceable thing called the standard. And is 1,4-dioxane along a trajectory to move from being a guideline to a standard?
Not that we know of, no.
Okay. Okay.
Yeah, I mean, it's, it's a guideline, and that's the way it's been used, and there's been no talk about making it a standard, but, essentially, there's no, I mean, there's really no, I mean, there is a difference, I've heard you talking about, but, I mean, we do, the drinking water program does have its risk limits, of 10 to the minus 5.
Yes.
So, essentially, it's regulated more or less, within the same range that the MCLs are, which are, they are within the range of 10 to the minus 6 and 10 to the minus 4, I should say, 1 in a million and 1 in 10,000. And our drinking water program risk limit for long-term use of water is 1 in 100,000. So even though it's not a standard, it's a guidance number. But if it occurs in a water supply above the ORSG, then an evaluation needs to be conducted. And if it exceeds the 1 in 100,000, then the drinking water program.
So the things that now have MCLs, did they used to be guidelines and over time they became enforceable standards? Or
No,
not?
most of the MCLs are directly from the EPA.
Okay.
There is one standard for one chemical, I think it's perchlorate, that started out as a guideline, as an ORSG. And that was a long process, and it finally turned into a guideline, a standard, an MCL.
But that doesn't sound like that's the normal path.
It's not the normal path.
Okay, thank you. Okay, Ginger.
Hi. Since the well that I understand nuclear metals was required by EPA or by Superfund law to drill, that was for the dioxane that was going towards the Acton well, why not require them to do a second one that would capture the plume that apparently might detach from the larger plume, but is closer to the well?
So the question is, there is an extraction well, which is perhaps seems to be beginning to split the plume, and why was there not a second extraction well required closer to the production well to capture the additional dioxane?
That would still be left there.
Dioxane.
Great question. We asked the same question, but at some point, the wells start to interfere with one another. So there was a well that was drilled in closer proximity to the Assabet 1A well. There was talk of whether or not that could be used for an extraction point through some of the groundwater modeling that's been done. It is believed that that would not be an effective use. So to put things in perspective, we're extracting 350 gallons a minute out of the Assabet well. I believe they're currently pumping around 12 or 14 gallons a minute out of the extraction well. So if you think about, the magnitude of 350 versus 10 to 15, our well is just going to continue to outpace what that other well can extract.
Thank you.
Richard Kelleher again. I have been made aware that the WR Grace settlement for the Superfund did not include the issue of dioxane. Is there any plan to try to get that under control? I know it's hard to control a very dispersed pollutant, and I'm just wondering whether, I've heard nothing tonight about a strategy for addressing that.
So our strategy has been to ask that the record of decision for the WR Grace site be reopened to address 1,4-dioxane. So right now, that record of decision says nothing about 1,4-dioxane. The fact that it's being sampled for and a treatment system was installed for it is only because Mass DEP was regulating that as a discharge, not as part of the cleanup. So the district has asked that that record of decision be reopened. The immediate response was, we can only do this during a 5-year review. Unfortunately, by the time we asked that question, they had just completed their 2014 5-year review of the site. So in 2019, that conversation can be started again.
Okay.
Yes, Tara Fredericks, West Acton. I don't even know if it's on.
It's on.
Doesn't make noise.
It's not on? Okay. Tara Fredericks, West Acton. It's my understanding, I was a selectman when we settled on the WR Grace, and it's my understanding, this is a comment, and then I'll get to my question, that I asked before I would vote to settle whether or not, if new information or new damage or harm came forward, that we discovered something else, could we reopen the litigation? And the lawyer said yes. So I feel like there's, yes, the DEP, ordering them to do something, but there's also the costs on our side that I think that we should go collect. So that's my next question. Relative to 1,4 dioxane, it's my understanding that California has much stricter, and I just came in, so you may have already answered this, much stricter standards to the tune of like, it's a 0.1, it's a magnitude of difference, that they require less than the standard that's currently in play in Massachusetts. And I'd like to comment, like, why aren't we working toward what California says is the minimum? Because the writings, the technical writings that I was reading in California were indicating that this was the minimum that we're going to go for even stricter
So the
standards.
question is, what is the California regulation, and is it stricter or?
It is stricter, and is and
Let's
why?
ask that as a
Oh, all right,
question
yes.
first,
Okay, first.
California standard.
Yeah, I don't know it off the top of my head. Are you looking it up?
I'm looking it up.
Yeah, did
I
you
think
say
it's one.
0.1? 0.1 as opposed to 0.3?
Yeah, I
Let's
think it's
just see what it is.
1.0.
I don't know what what is it?
I believe it's 1.0, not 0.1.
Yeah, it might
I
be.
could be
Dan's
wrong.
looking it up. Yeah.
Right, yeah, I think we
I-
have one of the lowest ones.
Yeah.
but
Yeah,
okay,
I-
thank you.
1.06 in my mind as well, but we're going to get the answer courtesy
Okay.
of Mr. Google
In,
here.
in the, again, the lab analytical, the way that we actually identify how much dioxane is in the water, is only reliable to 0.2. So to be below that, you'd really get into a, question of, is this even valid?
Thank you.
So.
Yeah, I mean, the website I'm looking at, the California Water Board website says 1 microgram per liter, which
Yeah.
is higher than Massachusetts.
Hi, my name's Joe Robb. I'm from Acton, and I've been following this off and on for the past few years. I actually worked with ACES on this and supported them in the past, and in fact looked at some of the groundwater modeling. And the fact, Matt, that you mentioned that the 5-year review's coming up, that's a time when lots of reports are going to be written, a lot of analysis is going to be done. My question to you, and I guess to Green Acton as well, is do we have the human resources to review those materials when those become available?
That's a great question, Joe. So one of the big pieces that I think will be coming out of the 5-year review, hopefully, is the 2 Superfund sites have been working for probably the past year and a half to integrate their groundwater model into one. So I believe that is going to be a huge deliverable that we will then have access to. We have been working with a consulting firm since 2015. So I believe that we would continue to lean on their support to help the district with our HR need for assistance.
Are you available?
I'm not pitching.
So, can I ask though, when you have the combined hydrologic model that combines the NMI and the WR Grace hydrology together, what kinds of insights are you thinking that would give us?
So right now, our understanding surrounding these wells is largely predicated on the WR Grace modeling.
Yep.
And as we know, Assabet River is a hydraulic boundary, is a prime example.
Yep.
That was a poor assumption. So really, we want to know, with more information, with more data, with better assumptions going into the model, what is that area contributing to our wells, and should we be looking at other places that we're not looking right now? So that's the kind of insight. And it will also help us understand what is the risk from this more diffuse WR Grace point.
So one of the things, I'm doing
ahead,
this right now.
please.
So one of the things that that we might learn from those model, that better model,
Yep.
that more complete model, is how much of the water that is getting to Assabet 1 or the Assabet River, the Assabet wells is coming from where.
Right.
So it's, when they combine these models, it's going to sort of look at, if you can sort of think of a big area around the well fields as 360 degrees, these models will probably give us sort of an understanding of, you know, maybe 180 degrees or less, 120 degrees, because they're not going to be telling us what's going on to the south and west, or
Yeah,
you know,
yeah.
over
There's
by-
no monitoring.
there's no data over there,
Yeah.
and that's not been their job. But
Good.
but we'll, so that they can use particle tracking to try to figure out how much water is getting to the well from
Yeah.
which parts of the aquifer in the area that they know something about, and they can also tell something about travel time from places. But you know, so that's the kind of stuff that we might learn.
That's exciting. So. Well, seeing nobody else at the microphone, I'm going to say I am extremely impressed at the quality and quantity of questions that you guys came up with and the quality of the answers. And I have small thank you gifts for our three speakers.
It's a green acting sweatshirt.
This is Thank you very much.
Do you want to make a pitch for folks who are interested in this stuff and talk to Green Acton?
Yes, Green Acton. It's a wonderful organization. We have committees that deal with energy, with materials, with land use, and with water. Green Acton has general meetings on the second Tuesday of every month at 7 o'clock at the library. They're open to anybody. The Acton Water Committee has meetings on usually on the second Sunday of the month at 2:30 in the afternoon at the library. All of those are announced on the Green Acton website. Sitting in the back is our fearless president, Deborah Symes, and you can ask her questions about Green Acton or ask me as well. And again, thank you all for coming.
I'm going to say thank you very much.